monostable multivibrators. I will move a bit faster on this one because already the base, we know the basic. We will see the detail of monostable multivibrator using the same agenda. We will see the definition and design components, and then we will see the circuit construction and operation, and we will see the output waveforms, formulas, and applications. So here monostable multivibrator is also using same building blocks. We have A1, A2 amplifiers or amplification stages, and we have the coupling networks. One is connecting two amplifiers, another one is connecting the feedback loop, or we are using in the feedback loop. We also have two outputs, output 1, output 2. And here we are using trigger signal. Okay, we will see that when we see the circuit construction. Amplifiers A1 and A2, so they are providing 180 degree phase shift, so that is okay, and also it's providing amplification gain. And this coupling network is nothing but combination of R and C network. We are using just resistors and capacitors to connect these two amplifiers, or maybe two transistors in our example. And A1 and A2 can be either transistors or operational amplifiers or 555 IC. Remember, in monostable, it's also two-stage amplifier. It produces two states, either logic 0 or logic 1, logic high or logic low, two states. So it produces two states. One state is stable and another state is unstable or temporary. So this is the monostable. So monostable have two states, 0 and 1. One state is stable, another state is unstable. So from stable state, if you want to change to unstable, you must give a trigger signal. Then it will go to unstable. Temporarily, it will stay in this state for a while, and then it will jump back, or it will return to stable state again here. So you need only one trigger signal to change from stable to unstable. And then it will automatically come from unstable to stable by itself. Okay, the goal is, of course, we are going to generate non-sinusoidal waveforms. And when we give trigger pulse, it changes from stable state to quasi state or temporary state. Circuit remains in quasi state for certain time, which is determined by the circuit elements R and C values. R and C. Then it returns back to initial stable state again. So now we will see the circuit. This is the circuit design of monostable multivibrator. Only one state is stable. So here you see the circuit construction more closely. Two transistors Q1 and Q2 are connected back to back. Even though they are identical, they are using different doping levels. It means they will not have same conditions at the same time instant. Even though you apply plus 5 volt or plus 12 volt at the same time, and maybe first Q1 will be on, Q2 will be off. So when we give VCC, both transistors will not be on at the same time. This is the purpose. We are using two identical transistors, two symmetrical transistors, but with different doping levels. Okay. Collector of Q1, collector of Q1. Q1 is here. This is the collector and this is the emitter. And this is the base. And here also the same base, collector. This is the collector terminal and this is the emitter terminal. Okay, collector of Q1 is connected. Collector of Q1 is connected to the base of Q2. Similarly, the collector of collector of Q2 is connected to the base of Q1, and of course via R2. So here we are connecting this collector via R2 to the base, and here also the collector via this C1 to the base of this Q2. R1 and C1. So here you see the two elements R1 and C1. R1 and C1 decides the time period for Q1. So how long this Q1, okay, this is the time period of Q1. So how long it will take to charge this Q1. Once it charged fully, then it will drive the base of Q2. Okay. So here we have some kind of capacitors. You can see here we have the C1, and here also we have another capacitor C. You should note down one more thing here. I am applying minus VBB to the base of Q1, and I'm also applying the trigger signal via C2 to the base of Q1. So this is something different from the previous circuit. So especially you should note down this one. This is called a trigger signal I am externally applying to this circuit, especially to the base of Q1. So here, what is the use of this C1? Where is C1? C1 is here. C1 is providing AC coupling. So this is actually, we can call this as a coupling capacitor. So particularly this is called AC coupling capacitor. AC coupling. So what does it mean? AC coupling means, so it will filter out DC components. So it will take out, it will be acting like a low pass or high pass filter. It will remove all the DC impulses, and then it will supply the pure filtered voltage to the base of this transistor. And also we have the DC coupling. That is, this C2 is called a DC coupling capacitor. So this is mainly helping us to give the trigger signal. What is the trigger? I already told you trigger means what. So it's like a large amplitude, short duration. So if you see this one, the amplitude, maybe it's a plus 5 volt or whatever, it's up to the designer. And the time period is just like a, maybe it's fraction of microseconds. Maybe it's this is the T value. This T is a very short time period. If you talk about the x-axis, and this is the y-axis. So this is the amplitude and this is the time period. The time period, we are applying this trigger signal for a very short period. Maybe this is for 0.1 microsecond. So large amplitude, short duration. This is called a trigger. Okay. So trigger, it passes all the signals from 0 Hertz to maximum bandwidth. So whatever you apply here at this terminal, this will all the frequencies. Okay, I apply 5 volt, right? So this 5 volt also have certain frequency. So it passes all the frequencies and it will drive the base of this Q1. So now we have both AC coupling capacitor and also DC coupling capacitor in this circuit. So this is the circuit construction. The circuit construction, nothing but we have the R1 C1. This is helping us to drive the base of Q2. And we have this RL1 and RL2. These are low value resistors which are helping us to make the biasing stability of the transistors. This is a standard one that we are using. Other than that, we have this coupling capacitor C. So what this one will do, we are getting output from this collector to this terminal, right? This is the output. So this capacitor will block all the unnecessary impulses and it will give the pure output at the output terminal. For example, I want only logic 0. So I do not want to have any impulses. So this will filter out all the impulses and it will give only pure logic 0, and then it will give pure logic 1, pure logic 0. So this is helping us in a way. to get the pure output. And here we have the DC coupling capacitor, and here we have the AC coupling capacitor. The purpose is just like it will act like a filter and filter out all the unnecessary impulses and unnecessary components, and it will give the only necessary voltage at the output of this capacitor. Now circuit construction is finished, and we are applying external trigger here. So now we will see the circuit operation. Now let us assume VCC is applied. We apply the VCC, and also I apply minus VBB to the base of Q1. So this will drive this Q1 is in off condition initially. Okay, let us say here now, step 1. So what I'm doing here is Q1, and then the collector of Q1, that is the output 1. Here I indicated with the letter A. So this is output 1. This is A. A is nothing but a collector of Q1. And I have Q2 transistor, and I have the output 2. Output 2 I indicated with the letter. The node name is B. So this is a B. So remember, A is the output of Q1, B is the output of Q2. And or we can also say this is the collector of Q2 and this is the collector of Q1. So what I am telling here in the operation, so first I apply this minus PBB, so this Q1 is off. Let us make the divider so we will not get mixed up. Let me take the pen, another pen. So, okay, one more. So Q1 is off. Okay, so now what will happen? So if the Q1 is off, then this transistor is in cutoff region. It means open circuited, right? If it's off, it means open circuited. So whatever the voltage coming from this VCC, it will accumulate into this node A. So this will be logic 1. So output here as logic 1. So open circuit, and now collector voltage of Q1 will raise and it will drive the base of Q2 via C1. So now this logic high, the high voltage, will be charging this capacitor C1. So once it's fully charged, then definitely this will drive the base of Q2. So now let us say if this is charged, then what will happen? This is logic 1. This logic 1 will drive the base of Q1. If we give the high voltage to the base, then this transistor will be on. So Q2 will be on. If the Q2 is on, there is a short circuit. So whatever the voltage accumulated from this VCC at this node B, it will go to the ground. So it means there will be no voltage here. It will be, the potential will be 0. So this is logic 0. So that is logic 0 at the output 2 terminal. So we get logic 0 at the output. If you make a graph, then let us say this is the x-axis and this is the y-axis. Let me take another color. So I have a logic 0 at the output. This is a 0 volt and this is a 5 volt. This is the step 1. In step 2, what is happening? In the step 1, right now, what we are doing, this Q1 is off and Q2 is on. So we get output. At the output, we have this output 1 at node A. We have the logic 1, and the output at node B, we have logic 0. So now Q2 is on. So this is the one we had seen. So remember Q2 is on, so its collector voltage will decrease. So this low voltage will drive the base of Q1 and it will remain Q1 is equal to off. So we know this one is logic 0 at this node. This 0 will drive the base of Q1. So the 0 volt cannot turn on this Q1. Though this Q1 is remaining, it's remaining in off state. Where is that? I mentioned somewhere here. Yeah, so it will remains in off state. So Q1 is in the off state. So this is the stable situation. This is called a stable state. So O1 is node A is 1, node B is 0. And this is a stable state. This circuit will give this output forever. Now I want to change this stable state into another one, unstable state. So how can I do that? So now if I apply a trigger to the base of Q1 via C2. So here I have the trigger. I apply the trigger to the base of Q1 via the C2. Then what will happen? This Q1 will immediately turn on. So you see here the second step, Q1 is turned on only if I apply the trigger. If I don't apply the trigger, then this will maintain the step 1. So because of the trigger, now I turned on this one. So if I turned on, there's a short circuit, then the current flow, whatever the voltage accumulated at this node from VCC, this will go to the ground. Then the voltage at this node A will be 0. This node will be 0. This is the node A. Okay. So now what is happening? We are making this as a 0. Its collector current decreases, which will drive the base of Q2. So now what will happen? Here we already said the voltage is 0. This 0 volt will drive the base of Q2. So 0 volt cannot maintain the on condition at this Q2. Then immediately there will be open circuit. So there will be no current conduction. So whatever the voltage accumulated at this node from VCC, it will accumulate, it will raise. So it will become logic 1. So now the voltage at this node will be logic 1. So now it will become logic 1. So, okay, remember here this 0 volt, because of this 0 volt, Q2 goes to off. Q2 go to off. Because of the Q2 is off, we get logic 1 at the output of at node B. So now this is what happening. Then the collector current increases, then we will get high voltage at the output of Q2 at node B. This is a quasi-stable state due to trigger signal. It's because of the trigger signal. So time period of this temporary state is determined by R1 and C1. Let me say, what does it mean? So now this is what happening in the second step, right? In the third step, what will happen? Let me change my pen color. This is the step 3. The step 3, what is happening now? Let us see here. So in the meantime, so now we remember this at node A, we have the 0 and node B, we have logic 1. So here you can see here. So at the same time, this VCC is charging this C1. So this C1 is charging. Until C1 is charging, this one will maintain the state of state. So once this C1 is fully charged, it will start to discharge the current, electric current to this base of Q1. Then this once we get enough voltage at this base, then this Q2 will go to on condition again. So this Q2 will go to on condition. It's because of the charge from or the electric current from this C1. So once it's on, then this high voltage will go to the ground. Then this will become logic 0 again. This will become logic 0 again. So the output of the Q2 will be 0, right? So this will become 0. So you can see here in this table, the output at the terminal B or node B is 0. This 0 volt will drive the base of Q1. Then the Q1 will immediately go to off. The Q1 will immediately go to off. So if it goes to off, then what will happen? This is the open circuit. Then the current, the voltage will accumulate at this node. Then it will become logic 1 or the high voltage. So then this will become 1. This is the step 3. This will maintain this condition. So now we have the logic 0 at this node and logic 1 at this node. Logic 0 at this node and logic 1 at this node A. This is node A and this is node B. So this is the stable state and this is the unstable state. So now we automatically, you see here, we give only one time the signal, then we give only one time the trigger signal, then from the stable state it becomes unstable. So it changed to Q1 is on and Q2 is off. But after some time, based on the charging time of the C1, then automatically this on become off and this off become on. Now this circuit will maintain this step 3 condition forever unless you give the trigger signal. So this is the step 3. So this will happen alternatively again and again. So it will maintain the stable state. This is the stable state and this is the stable state. Now if I want to change to the unstable state again, then I have to give the trigger signal. That is the step 4. So this is why we call this as a monostable multivibrator. So please remember, this is the circuit operation. So when you apply the first time the voltage, and also here we are also applying this VBB. So we are maintaining the off condition of the Q1 and on condition of the Q2. Based on the on or off, you are accumulating the voltage from VCC at this node, or you are dropping this accumulated voltage to the ground. Based on that, you are tapping the output. So it can be either logic 0 or logic 1 or logic 0. So one state is stable. This is a stable state. If you want to change to unstable, you are giving the trigger, then immediately this Q1 will turn on and it will be temporarily on for some time. Once this one is fully charged, then this will drive here, then it will go to, so the opposite operation will happen. So this is, I have explained everything here in the wordings, in the paragraphs. When you read this, you will also understand this operation. Or whenever you this normally in the stable mode, Q1 will be off and Q2 will be on. This is a stable mode. So because of this, we get the logic 1 at the output and the logic 0 at the output here. But if you want to change from this stable to unstable, then you apply the trigger signal, then immediately it will go to the opposite. This will be on and this will be off. If this is off, then it will become logic 1, and this is on means this will become logic 0. And based on this time constant value, then it will immediately start to drive this transistor after this capacitor is fully charged. Then this off condition will become on again. So if it's on, then the output will become 0 and this will become off again. If it's off, then the output will go to the stable state again. So this is one state is stable and another state is unstable. And output waveforms. So whenever you apply the trigger signal, the capacitor is starting to charge slightly, slowly and linearly. So once if it goes fully charged, or the discharging voltage, if it's more than the threshold value of this transistor, then it will turn on the other transistor. So anyway, so the temporary state is really based on the capacitor charging time. So you can read this text, but the output waveforms are like this. So always the Q1 and Q2, they are in the opposite operation. If Q1 is off, Q2 will be on, and in the other way. And then now we will see the formula. So after trigger, the temporary state time or the quasi state time period is up to the C1 charging and discharging time. So the time period of quasi state T1 is equal to, this is the formula, 0.693 R1 C1. This is same like the previous circuit design we had seen. The stable, because both states are not stable, so we have two timings, two temporary state timings. So where do we use this monostable multivibrator? So monostable multivibrators, this is the question actually, just like a multiple choice question. Do we use this monostable multivibrator for pulse generator, or we use this in pulse stretcher, or we are using this in pulse looser? In pulse generator means we are generating the pulse automatically like this. So in monostable multivibrator, we do not get the output like this. So if you want to change from one state to another state, we must give the trigger. So we are not using this monostable multivibrator in pulse generator. We are also not using this in pulse looser, but we are using this monostable multivibrator in pulse stretcher, because we are giving some kind of delay to one output. So for example, if this is in the stable state 0, and then when if we want to delay this little longer, then we just don't give any trigger. It just stays in logic 0. Now suddenly you give the trigger, then immediately it goes to quasi state logic 1 for some time, and then it will automatically go back to stable state again, and then it will stay here. So you can stretch this pulse in off state for a long period, and whenever you want, you can give the trigger signal, then it will go to logic 1 for shortly and then go back. So this monostable multivibrator is used in pulse stretcher. We are stretching the pulse. Okay, so now applications. So we can generate, or these monostable multivibrators are helping us to generate delay in timing circuits, and it's also used in temporary memories to store data, and also it's helping us to trigger another pulse generator. And we are using these monostable multivibrators in television circuits and the control system circuits. So we are using these monostable multivibrators in different practical applications. Based on the application where we want to use, we can decide we want monostable or astable or bistable multivibrator. So these are the applications. Now we are done with monostable multivibrator.